So you can see the question: compute the tension capacity of an angle section Fe14 connected to a 10 mm gusset plate. We have done a similar kind of question, but we are going to do this for a welded connection. Okay, there is an IS angle 150 by 115 by H of Fe14 steel, which is connected to a 10 mm gusset plate. So it is like this. If you see the figure, it is like this. You can see this thing is connected to a there is a IS angle. This is actually an IS angle. We have to have an angle section like this. There is 110 mm weld over here and 100 mm weld over here, and there is a transverse weld of 150 mm. And you can see the longer leg is connected with the gusset plate. This is a 10 mm gusset plate. This is 10 mm. So, are you clear with the question? Are you clear with the question? You are supposed to calculate the tension capacity. So the tension capacity, as you know, the tension capacity of an angle section or a tension capacity of a member is what? Tension capacity, I can write it as, is the least value of what? It is TDG or TDN or TDB, right? Isn't it? So from here we need to calculate the value for TDG. This corresponds to 6.2 of your IS code. This corresponds to 6.3 and this corresponds to 6.4. Right? Now we will see one by one. First, that is, we need to say 6.3, 6.2. 6.2 is actually, as you can see here, TDG, that you know, TDG is equal to AG Fy by gamma m naught. So from here I can write 6.2. I can write from 6.2. I can write TDG is equal to AG Fy by gamma m naught. This AG value you will get it from SP16. AG value you will get it from SP6. That is AG I will get here as 2058 mm square, which means after calculation I will get this value as what is this is 2058 into 4, sorry it's not 4, 250. This is Fy 250, and from table number 5 you will get the value for gamma as 1.1, and when you compute this you will get the value for this as 467.73 kilonewton. This is, we have already done similar kind of questions many times, so I hope you are okay with this. Now the next one is 6.3, that is TDN. As you can see, TDN for an angle section, that is the design strength due to rupture of a critical section. You can see it is given in clause number 6.3.3. Right? It is given in clause number 6.3.3. So you can see the TDN value, I can write it as here, TDN is equal to what? 0.9 ANC, 0.9 ANCFU divided by gamma ml plus beta times A G naught Fy divided by gamma m naught. So here ANC means what? Can someone reply please? It's very difficult for me to. What is ANC here? ANC is the net area of the connected leg, isn't it? But here, when you compare with the bolted connection, there is no reduction in area due to bolt hole. So the gross area and net area, I can say both are same. Have you understood that? There is no deduction in area. It was like a bolted connection. Then definitely, if it was a bolted connection, you would have to apply some code over here. As a result, there is some reduction in area. But here, this case, it is actually a welded connection, so there is no reduction in area. So I can write ANC is what? ANC is the gross area itself, which means I can write ANC is equal to what? That is net area of the connected leg is what? 150 minus thickness by 2. Thickness is what? What is the thickness here? Thickness is given as 8, right? 8 by 2. So 8 by 2 into 8. Can you tell me this value? I haven't taken it. Minus 4 into 8. We get this as 1168. This is 1168 mm square. Similarly, AG naught. AG naught is the gross area of the outstanding leg. So that is I'll get this one as 115 minus 8 by 2 into 8. 115 minus is 111 into 8. 888 mm square, right? Have you understood this? So which means this ANC AG naught, Fy value you know, if you also you know, gamma m naught you know, gamma ml you know. Next one is the beta. So beta here I can say the beta is, the equation for beta is given by your IS code. You can see that is given by your IS code. Beta I can write it as beta is equal to 1.4. Beta is equal to 1.4 minus 0.076 W by T Fy by Fu and Bs by Lc. It should be less than or equal to Fu gamma m naught divided by Fy gamma ml and greater than or equal to 0.7. So you need to understand each and every term here. So what is W here? W is the outstanding leg width, which we can directly write as W is equal to, this is IS angle 150 by 115 by 8. So I can write this one is 115 mm. Thickness T it is given, it is IS angle 150 by 115 by 8, which means thickness is 8 mm. Thickness is 8 mm. Now BS as you see here in your IS code, if you see your IS code, you can see BS is the shear lag width as shown in figure. BS is given, you can see here BS is given as W plus W L minus T for a bolted connection, and welded connection you can see BS is equal to W, where W is the length of the outstanding leg. So I can directly write the BS is equal to W, and we know what is the value for W, that is 115 mm. 115 mm. Now the next one is LC. LC you can see in the code it is given. LC is given as, you can see LC is the length of the end connection, that is the distance between the outermost bolt in the end joint measured along the lower direction. This we have discussed in the class. And for a welded connection, it is the length of the weld along the lower direction. So you can see here it is the length of the weld along the lower direction. I'll be applying a tensile force like this. So the length of the weld which is available is 110 and 100. Either you can take the average of these two, or you can take the higher value. So I'll be taking the higher value, that is LC. I will take it as length of the weld along the direction of the load. So have you understood that? Students, have you understood? Do മനസ്സിലായോ?
Yes, sir.
LC എടുത്തത് മനസ്സിലായോ? So when you calculate the value for this, I'll get this as W by T into Fy is 250 divided by Fu, that is 410 into PS by LC. PS is 115 divided by LC 110. So I'll get the value for this beta after all substitution. I'll get the value for beta as 0.703. Did you get this value? I can calculate it. 703, which should be less than or equal to Fy Fu. Fu is 410 into gamma m naught, that is 1.1 divided by 250 into 1.1. Gamma m naught is what? Gamma m naught value is number 5. Gamma m naught is 1.1 and gamma ml is 1.25. So gamma m naught is 1 and gamma ml is 1.25. So this will get it as, this should be less than or equal to 1.4 and should be greater than or equal to 0.7, which means this is fine, right? So this value is fine, isn't it? Hello, Manslayo.
Yes.
So you'll get this value as 0.7. Now you got the value for beta, which means you could calculate the value for your TDN. TDN, I can calculate it as what? TDN is equal to 0.9 into ANC. ANC I got it as 1168 into FU, that is 410, divided by gamma ml 1.25 into again beta 0.703 into 8G0, that is 888 into Fy, that is 250, divided by gamma m naught 1.1. You get this as you get this as 486.671. I hope you do this. 486.671 kilonewton. So TDN value is now known to you. I hope you have understood this. Is it fine? Hello, okay now? Students, is it fine?
Yes, sir.
Now the third one, that is your T6.4, that is need to calculate the value for your TDB. So this is 6.2, 6.3. Once again. Next one is 6.4, that is the design strength due to block shear. So block shear strength, in order to calculate that, block shear strength I have the equation for block shear, that is 6.4. You see, I have TDB is equal to AVG. The equation is written here, so I will not repeat it again. I'll write it AVG Fy by root 3 gamma m naught plus 0.9 ATN Fu divided by gamma ml over this. I can copy this. Yes. So you have the equation like this. Your TDB is equal to this one, right? Now, if you see here, this is going to fail as this. When I am applying a load, it is going to fail in block shear as a whole like this. It is going to fail in block shear in this way. It is going to fail as a block when it is welded connection in this way. It's given in the code. You can see here can see here, this is actually for a bolted connection, but the code has given you the detailed specification here. For welded connection, the block shear strength TDB shall be checked for the welded end connection by taking an appropriate section in the member around the end weld, which can shear off as a block. Which means this is going to happen around the end weld, which can shear as a block. So what it infers is, it is going to go as a whole like this. Then a block it is going to fail. So if I calculate this, I have my AVG. AVG, I can say that my AVG is equal to, you can say, AVG means what? It is the V corresponds to your shear and G corresponds to your gross area. So the gross area which is resisting, the gross area of the weld we have to consider. The gross area which is resisting here is what? This much length into thickness is the gross area which is resisting here, right? So I can write the gross area AVG is equal to 110 plus 100, that is the total length, into the thickness of the section, that is 1680 mm square. Now this is the welded connection, so the gross area and net area along the tension side is same, so I can write AVG is equal to what? AVN. Similarly, I can write ATG, that is the load resisting along the tensile side, that is 150 length into thickness, that is 8, that is nothing but 1200 ml square. And here I can say this ATG is equal to what? ATN, since there is no deduction. So substituting the values for this, for AVG, FY as 250, gamma M naught as 1.1, ATN as 1200, FU as 410, gamma ML is 1.25, AVN is same as AVG, then FU is 410, gamma ML, and ATG is same as ATN. I'll get the value for this TDB. This value I'll get it as 574. This value I'll get it as 574.68 kilonewton, and this value I will get it as 559.06 kilonewton. So which means from all the four, the smaller of the value if I take, which is 559, 574, 486 and 467. So the gross yielding will be the least value, and as a result I can say it will fail in what? The design strength of the member, I can say it as this TD, I can write it as it is TDB, this TDG, which is equal to TDG, which is equal to 467.73 kilonewton. So have you understood this? മനസ്സിലായോ?